We've all seen those systems, right?
Hmm.
The ones juggling a dozen tasks smoothly all at once. Like your browser streaming video while downloading updates, maybe.
Yeah, or think about a bank handling thousands of transactions basically simultaneously.
Exactly. And that concurrency, it feels effortless. It's powered by multi-threading, gives incredible efficiency.
There's always a but.
Right. The moment those tasks need to touch the same shared thing, maybe some data or a resource,
That's when that smooth operation can just, yeah, turn into a real tangled mess.
it really is like uh, multiple people trying to write on the same whiteboard at the exact same time, isn't it?
That's a good way to put it. Multi-threading is fantastic. It makes apps responsive, efficient,
Hmm.
but it brings this fundamental challenge, coordination. How do they all play nice?
And that's precisely where Java's thread synchronization steps in. It becomes absolutely indispensable.
Hmm.
So for this deep dive, our mission is really to unpack it.
Hmm.
What is it? Why do we absolutely need it? How does it actually work, under the hood?
And maybe crucially, what are the pitfalls? What do you, the listener, need to watch out for?
Yeah. We've done the digging, sorted through the noise, pulled out the core ideas.
And we found some helpful analogies too, hopefully.
Right. Almost like designing traffic rules, but for your code,
Mhm.
to give you a shortcut to understanding this really fundamental concept.
Okay, so let's dive in then.
Yeah.
At its heart, Java thread synchronization, it's a mechanism. Its job is to control how multiple threads get access to shared resources.
Shared resources.
Yeah.
So that means things like variables or data structures, maybe even files.
Exactly. Anything that more than one thread might need to look at or change within a multi-threaded program.
And the why is, well, it seems pretty critical, right? Because threads share the same memory space.
They do. And without coordination, without some rules, they can just barge in and try to read or change the same piece of data simultaneously.
Which leads to chaos.
Pretty much. Inconsistent results, incorrect data. It's not just a simple bug. It can really undermine the trust in your entire system.
So synchronization is like the digital guardrail then. It ensures only one thread gets access at a time, prevents that data pileup.
That's the idea. It prevents that kind of data chaos. Think of it like a traffic light at a really busy intersection.
Okay. Well,
The light makes sure only one direction of traffic moves at a time, right? To stop collisions, keep things flowing.
Yeah.
Synchronization does the same for threads. It ensures they take turns accessing those shared resources in an orderly fashion. It's about setting up a protocol.
That traffic light analogy really clicks. So, okay, it avoids chaos, but why is it absolutely critical? What are the deeper implications here?
Well, fundamentally, I'd say it's about building trustworthy systems. A huge reason is preventing data corruption.
Right.
Without synchronization, you run straight into what we call race conditions.
Ah, yes, race conditions.
Yeah.
Where the result depends entirely on luck, basically, on the unpredictable order the threads happen to run in.
Exactly. And you definitely don't want your bank balance to be a lottery, right?
Definitely not.
Synchronization prevents that. It also ensures data consistency. It guarantees that shared data stays reliable, even if multiple threads are trying to modify it around the same time.
And when you stop and think, pretty much every complex, robust application must rely on this then.
Absolutely. You mentioned web servers earlier, handling thousands of user requests.
Yeah.
Or banking systems processing countless transactions. They depend on multi-threading, and therefore they absolutely depend on synchronization. Without it, they wouldn't just be buggy.
They just wouldn't work reliably.
They wouldn't be functional, period. Or certainly not reliable enough for what they do. It allows safe sharing for all sorts of resources, files, database connections, shared memory.
Without weird side effects.
Exactly, without unexpected behavior cropping up. The classic example, the one that really drives it home, is updating a bank account balance.
Okay.
Imagine multiple transactions, deposits, withdrawals hitting the same account. These are essentially different threads. Synchronization makes sure they don't step on each other's toes. It prevents one transaction from accidentally overwriting the changes made by another, which would lead to a completely wrong final balance.
So each operation becomes sort of atomic,
Yeah.
complete in itself before the next one starts on that date.
Precisely. Atomic and isolated. That's what synchronization buys you.
Okay, so we've got the potential chaos identified, and we see the critical need for order for these rules. But how do we actually implement this control? How do we tame the chaos? And what are the payoffs when we do it right?
Well, the biggest, most obvious benefit, as we've sort of touched on, is data integrity. Plain and simple.
Yeah.
Synchronization directly prevents those race conditions. It ensures shared data gets updated consistently, predictably. It brings order.
Predictability in what could otherwise be a very chaotic environment. Makes sense.
And for a really clear example, think about an online ticketing system for a popular concert.
Oh, yeah, those can be frantic.
Right. Synchronization is what stops two different people operating through two different threads from accidentally buying the very same seat at the exact same moment.
That would be a customer service nightmare.
Yeah.
Seat 14B sold twice.
Exactly. So it prevents that. It also makes your code inherently thread safe.
Thread safe. What does that mean in practice?
It means multiple threads can execute that piece of synchronized code concurrently without causing errors or inconsistent results.
Okay.
And that is crucial for reliable concurrent execution. It lets you build complex applications, things with parallel processing or really responsive user interfaces, and know they can run safely and efficiently.
So you get controlled access, which helps cut down on those really hard to find intermittent bugs.
Definitely. It provides a structured way to manage that access.
Now, it sounds like it could add complexity, though. Are there different ways Java lets you do this, or is it like one size fits all?
Oh no, Java gives you options. It has powerful built-in mechanisms. The way it works internally, it relies on this concept called a monitor.
I'm on
Yeah, you can think of it like an internal lock that's associated with every single Java object.
every object has one. Okay.
Yep. And when a thread wants to access a resource that you've marked as needing synchronization, well, it first has to acquire the lock for that specific object.
Ah, so it needs to grab the lock first. And the key thing here, I guess, is that only one thread can hold that lock, that monitor, at any given time.
Exactly. That's the core principle. Only one thread gets the lock. Any other threads that try to access that same synchronized resource while the lock is held,
They have to wait.
they have to wait patiently until the thread that currently holds the monitor releases it. It's like having a single key to a specific room.
Okay, I like that analogy, too. The room is the shared resource or critical code.
Right. Only the thread holding the key can enter the room. Everyone else waits outside until the key is returned.
So it ensures whatever happens in that room, whatever changes are made, they happen in isolation. No interference.
Precisely. And Java gives you two main ways to use this locking mechanism. You have synchronized methods and synchronized blocks.
Okay, what's the difference?
If you mark an entire method with the synchronized keyword, it means only one thread can execute that entire method at a time for any given instance of the object.
So if thread A is running a synchronized method on my object, thread B has to wait to run that same method on my object.
Correct. Or any other synchronized method on that same myObject instance, they queue up and wait their turn.
But sometimes you don't need to lock the whole method.
Right.
Maybe just a small part.
Exactly. And that's where synchronized blocks come in. They offer finer-grained control. You can use them to synchronize only a specific section of code within a method, the part that actually deals with the shared resource, rather than locking the entire method call.
And that sounds like it can be way more efficient.
It often is, because it reduces the amount of time that lock is held. Other threads might have to wait less, which can significantly improve performance, especially if the non-synchronized parts of the method take a while.
So the JVM, the Java Virtual Machine, is handling all this lock, acquiring and releasing behind the scenes, managing the queue.
Yeah, the JVM manages which waiting thread gets the monitor next when it becomes available. When a thread finishes executing the code inside the synchronized method or block, it automatically releases the monitor.
So the next waiting thread can grab it and proceed.
Exactly. It orchestrates that flow.
It's pretty sophisticated how much is happening automatically there. And while we're on the basics, is it worth mentioning the more advanced stuff briefly? I know there's more beyond synchronized.
Oh, absolutely. It's good to be aware that Java's java.util.concurrent package exists. It's full of more advanced concurrency tools.
Like what?
Things like reentrant lock, which is a more flexible lock, semaphore for controlling access to a pool of resources, countdown latch for coordinating thread startup or completion. Lots of powerful utilities.
So once you've got these fundamentals, the synchronized methods and blocks, down pat,
Then exploring java.util.concurrent is definitely the next step. Those tools offer more control, often better performance, and ways to handle much more complex synchronization scenarios.
okay, good to know there's a deeper level. It's like a whole toolkit.
It really is. It's an incredibly powerful system built into Java, designed to handle some really complex concurrent situations.
It sounds amazing, honestly. Powerful, solves huge problems, almost like a magic wand for making concurrent code safe.
Uh-huh.
But I'm guessing, like any powerful magic, there've got to be some downsides, some curses if you're not careful. What are the big traps people fall into with synchronization?
Well, yeah, you're right to be cautious. The first major thing to think about is performance overhead.
Ah, okay. How so?
Synchronization isn't free. It introduces a cost because, well, threads might have to wait for that lock.
Right. Waiting means not doing work.
Exactly. That waiting can slow down the overall execution. It can potentially reduce or even eliminate the very performance benefits you were hoping to get from using multithreading in the first place.
So you could actually make your program slower by over-synchronizing.
Oh, absolutely. If you synchronize too much or hold locks for too long, you can definitely end up with performance worse than a simple single-threaded version. It's a balancing act.
Yeah, that makes sense. If everyone's stuck waiting in line constantly, nothing moves fast.
Hmm,
Okay, what else? I feel like there's a big one looming.
there is. The dreaded D word, deadlock.
Ah, deadlock. I've definitely heard horror stories about programs just freezing, completely locking up.
That's exactly what a deadlock is. It's a really critical problem in concurrent programming. It happens when two or maybe more threads get stuck indefinitely, each waiting for a resource that the other thread holds.
Can you give an example?
Sure.
Yeah.
The classic scenario is, imagine thread A acquires lock 1 and then tries to acquire lock 2.
Okay.
But at the same time, thread B has already acquired lock 2 and now it's trying to acquire lock 1.
Uh-oh. I see where this is going.
Yeah. Neither thread can proceed. Thread A needs lock 2, held by B, and thread B needs lock 1, held by A. They're stuck in an unbreakable cycle, waiting for each other forever. The program just grinds to a halt.
Wow. And I bet those are incredibly hard to debug.
They can be nightmares, especially because they often only happen under specific timing conditions or heavy load. I remember once spending, seriously, almost a week tracking down a deadlock bug that only appeared intermittently in testing. It turned out to be a really subtle issue with lock ordering. Not fun.
Yeah, it sounds like the kind of thing that keeps developers up at night and really highlights another potential pitfall, doesn't it? The sheer complexity.
It does. Designing concurrent code that uses synchronization correctly requires really careful thought and planning to avoid issues like deadlocks, race conditions.
Mm.
It's not trivial.
Especially for beginners, I imagine. Trying to get the synchronization right, but also worrying about performance. It must feel like walking a tightrope.
It can initially. And related to that performance aspect is scalability. If you overuse synchronization or use coarse-grained locks excessively.
You limit how well the application can scale up.
Exactly. As you add more threads or more users, if they're all constantly waiting for the same few locks, you hit a bottleneck. They spend more time waiting than actually doing work, so adding more threads doesn't help or even hurts.
Okay, so performance hits, deadlocks, complexity, scalability limits. Any other gremlins hiding in there?
Well, there are other related liveness problems. Deadlock is the most famous, but you can also run into things like starvation.
Starvation, like a thread never gets its turn.
Sort of. It's where a thread is technically able to run, but it's repeatedly denied access to the resources it needs, perhaps because other threads keep getting prioritized for the lock, so it starves and never makes progress. And then there's live lock. That one's a bit weird. It's where threads aren't blocked, they're actively doing things, usually responding to each other.
But they don't actually make any real forward progress, like they're stuck in a loop of reacting.
Exactly. They're busy but going nowhere. It's less common than deadlock, but still a potential issue in complex systems.
Okay, wow. So there's definitely a dark side if you're not careful. Knowing all these potential problems, the overhead, the deadlocks, the complexity, what's the core takeaway for someone just starting out with this? What's the action plan for a beginner?
Yeah, it sounds daunting, but it's manageable. I think the fundamental insight isn't just how to use synchronized, but learning to see where the danger lies, learning to identify that shared mutable state data that multiple threads might change as the potential trap.
So spot the shared data first.
Right, and the consistent advice is start simple. Don't try to get fancy right away. Focus on using synchronized methods or maybe small synchronized blocks just to get the hang of protecting those critical shared resources. Master the basics first.
And part of that basic understanding is really getting what a race condition is, right? Learning to spot those specific situations.
Absolutely crucial. You need to actively look for places where multiple threads might try to access and modify the same piece of data concurrently, like updating a shared counter or modifying a shared list.
Because those are the exact points where you need synchronization to avoid inconsistent results.
Precisely. Identify the critical sections.
Okay. And then thinking about the performance side.
The key is to use synchronization sparingly. Apply it only where it's actually needed to protect that shared data. Ideally, you want to make your synchronized blocks as small as possible, covering only the truly critical section of code.
Minimize the time the lock is held.
Exactly. Just enough protection, not a total lockdown of everything.
And what about avoiding those deadlocks? Any practical tips?
Definitely. A common strategy, especially if threads need to acquire multiple locks, is to always acquire them in a consistent, predefined order.
So if you always lock resource A, then resource B, you avoid the situation where one thread has A waiting for B and another has B waiting for A.
Correct. Consistent lock ordering breaks that potential cycle. Another technique is to use timeouts when trying to acquire a lock. If you can't get the lock within a certain time, you back off and maybe try again later or signal an error.
Okay, that sounds useful. And once you're feeling more comfortable?
Then it's definitely time to explore those advanced utilities we mentioned in java.util.concurrent.
The reentrant lock and things like concurrent hash map.
Yeah. They offer more features, more control, and often better performance characteristics for specific situations compared to the basic synchronized keyword. They're like the next level tools.
Got it. What else is key for beginners?
Testing. Oh my goodness, testing.
I bet. Because concurrency bugs are sneaky.
Incredibly sneaky. Multi-threaded programs, especially with synchronization, can behave differently under different loads or timing conditions. You absolutely need thorough, robust testing. Stress testing, different scenarios.
Yeah.
Try to shake those bugs out before they get into production.
Sound advice. Anything else?
One more thing. Look into thread-safe alternatives sometimes. You don't always need explicit synchronized blocks.
How so?
Well, Java provides some data structures that are inherently thread-safe, like concurrent hash map or copy-on-write array list. Using those can sometimes eliminate the need for manual locking around collections.
So the data structure handles the concurrency control internally.
Right. Also, using immutable objects, objects whose state cannot be changed after creation, is a great strategy. If data can't be changed, there's no risk of race conditions when multiple threads read it. Less need for synchronization.
Interesting. So sometimes you can design the problem away rather than just locking everything down.
Exactly. It's often a cleaner and safer approach if it fits your use case.
Okay, this has been incredibly insightful. So just to recap our deep dive here, Java thread synchronization, it's clearly a powerful, really indispensable tool.
Essential for ensuring data integrity when you've got multiple threads running in your Java programs.
Right. It's what lets us build those reliable concurrent applications that juggle lots of tasks efficiently without descending into chaos.
But, and it's a big but, it absolutely requires careful thought and application. You have to be mindful to avoid those performance bottlenecks and those really complex, hard-to-debug bugs like deadlocks.
It really is an art, isn't it? Finding that delicate balance between ensuring safety and maintaining good performance.
It truly is. It takes practice and understanding.
So for you, the listener, your journey ahead, if you're working with Java concurrency, should probably start with those simpler scenarios. Get comfortable with the basics.
Yeah, and then gradually explore the more advanced tools in java.util.concurrent as you gain more experience and encounter more complex problems.
Because mastering this isn't just about writing code that runs slightly faster. It feels much more fundamental than that. It's about building Java applications that are genuinely robust, reliable, and trustworthy.
Absolutely. It's a cornerstone of solid concurrent programming in Java.
Which leads to a final thought to leave you with, something to chew on. Considering all these complexities, the benefits, the pitfalls we've discussed,
How might a deeper understanding of human social coordination, things like traffic management systems, or how teams collaborate on complex projects, how might that understanding inform the way we design more robust and maybe even more efficient synchronized software systems in the future?